Hello, my name is Clement Fung, and I'm a PhD student at Carnegie Mellon University. I'm presenting on behalf of my collaborators, Chris Yoon and Ivan Beschasnik from the University of British Columbia. Federated learning is a popular technique for distributed machine learning, and in this work we show ways in which sybils can be used to attack federated learning. We're all aware that machine learning is a popular application and is making breakthroughs year after year. However, this progress does not come for free. Machine learning requires both large volumes of data, data from a diverse array of sources, and data that is collected recently. With this increase in requirements surrounding the data collection and model training process, the infrastructure behind such techniques has also evolved. Previously, centralized training, in which data is collected and concatenated on a server's cloud, and then machine learning is run on this dataset, is no longer sufficient for the large training datasets used in modern applications. This has birthed distributed training. In distributed training, clients also send their data and they are stored on the server domain, and a parallel machine learning process occurs over these sharded datasets and sharded workers in the server's system. The next evolution of this system, as requirements have continued to evolve, is federated learning, a technique developed by Google in 2017. In federated learning, rather than sending data and collecting it over the network, the machine learning process itself is performed over the network. There is no need to transfer data to the server's domain, and this greatly reduces the cost on the network. The server is now reduced to an aggregator. Since the machine learning process occurs over the network, the server just aggregates model updates as they are sent in from clients. This has provided wins in privacy preservation, where techniques such as differential privacy and cryptographic secure aggregation have made their way to federated learning, and also has the additional win of enabling training over non-IID data settings, where IID means independently and identically distributed. What this means in practice is that a machine learning setup can be established amongst users with highly disparate data. A user could have photos of just dogs, another user just cats, another user just fish, and a global model can be trained across these data sets that satisfies a global learning objective. This is important because any individual client's dataset would not be able to supply this objective, but federated learning enables training over this data setting. This has caused a spark of interest in domains such as mobile and the Internet of Things, and applying federated learning to those settings. However, there are drawbacks to federated learning. Federated learning opens a new threat model. Because data is no longer supplied to the server domain and clients are no longer just passive data providers, clients have the ability to perform arbitrary compute before sending updates to the federated learning aggregator. The aggregator never sees these client datasets, and the compute occurs completely outside its domain. This makes it very difficult for clients to be validated, especially in a non-IID setting. It is difficult for the server to determine whether or not updates being sent in from clients are genuinely produced from a machine learning process, or if they are the product of a malicious adversary. In a traditional poisoning attack, an adversary joins a machine learning system and supplies malicious training data to the model such that the final behavior of the trained model is manipulated. As an example, see this two-class classifier that is just separating the dark squares from the light triangles. Now an adversary joins the system and inserts some malicious data points into the training dataset. When a new classifier is trained, you'll see that the decision boundary is significantly altered. And the key objective here is that now the adversary has caused a new model to be trained that misclassifies a target training example or test example. And this is the goal of the poisoning attack, to supply poisoned training data to manipulate the final trained model. In federated learning, one can use sybils in a similar way to perform the poisoning attack. Whereas now, instead of providing malicious training data, one can join the system as a malicious user and provide malicious model updates to perform the exact same objective. One key difference in federated learning, though, is that since users join the system and there are no assumptions about how this occurs, a system that allows the creation of sybils, fake accounts to increase the influence the adversary has in the system, allow the poisoning attack to become even stronger. This is made even worse in the non-IID setting, where data representation is sparse amongst clients. As an example, we'll show a 10-client non-IID MNIST setting. MNIST is the digit recognition task well known in machine learning that just aims to identify what digit from 0 to 9 an image is showing. In this setting, we are non-IID, so this means that each client holds only one digit of the original MNIST dataset, and thus there are 10 clients, one for each label. Let's assume that an attacker joins the system and wants to poison this model. For example, they may want to have all ones misclassified as 7s by the eventual trained model. You may think that at least 10 sybils are required since the honest clients need to be overpowered in this system. However, due to the sparseness of data in the system, only 2 sybils are required to perform a successful poisoning attack. 96.2% of ones are misclassified as 7s in the final model. Additionally, you'll notice that the accuracy of digits that are not 1 are minimally changed. The accuracy only drops from 90% to about 88.8%. And this is one of the things that makes poisoning attacks or targeted poisoning attacks very difficult to detect. In MNIST, there are 10 classes, so this may be easy, but in larger machine learning models where there are hundreds or thousands of classes, it will be difficult to detect these attacks at scale. Thus, our contributions are, first, we identify this threat to machine learning, to federated learning, and a gap in the existing defenses in federated learning. We show that no prior work has studied the problem of sybils in federated learning, and broadly categorize different attacks and strategies that sybils can use when attacking federated learning. This is done along 2 dimensions, the objective of the adversary when creating sybils, and the capabilities that each of these sybils may have. In the second half of this talk, we will discuss FoolsGold, a novel defense that we've designed against Sybil-based poisoning attacks on federated learning. FoolsGold specifically is aimed to defend against targeted poisoning attacks, and has the benefits of both preserving the performance of federated learning in a benign setting, as well as preventing poisoning from an increasing size of a Sybil adversary. We show in our work that even with 99% adversaries, FoolsGold can prevent a poisoning attack. Now we will discuss the space of federated learning and ways in which Sybil attacks, existing defenses, interplay, and new opportunities from these experiments. There are many types of attacks on federated learning. We've demonstrated, for example, that poisoning attacks fall under the classification of any attack that affects the quality of the final trained model. We also discuss other attacks shown in prior work, such as privacy attacks, where honest client datasets are de-anonymized, or utility attacks, where the utility payout assumed in the federated learning system is manipulated. Both of these types of attacks are shown in prior work. A new attack developed in our work in this paper is training inflation. This is an attack where sybils join the system with the goal of occupying shared resources. Perhaps the federated learning is running on a shared cloud, and in this case, the sybils want to maximize the time taken, the network bandwidth, or the usage of shared GPUs in the system. Current defenses for federated learning are unable to handle this wide variety of attacks. Existing defenses for federated learning, such as multi-crumb, Boolean, or the trimmed mean and median, are essentially aggregation or summary statistics. They all make the assumption that some summarizing statistic is the best estimator of benign behavior in a federated learning system. They additionally require a bounded number of attackers when considering their defense, and thus are unsuited to handle Sybil attacks. As well, since these attacks all focus on poisoning attacks or broadly model quality attacks, they don't handle other attacks proposed in our work, including training inflation, the new attack we've proposed. As an example, we execute the following defenses in federated learning against a targeted poisoning attack of increasing proportion. As the number of poisoners increases in the system and exceeds the defined theoretical bounds that these defenses provide, the attack rate is very high, meaning that the poisoning attack has succeeded with high effectiveness. Conversely, FoolsGold, which is designed with sybils in mind, does not have an explicit bound on the number of attackers, and thus is robust as the number of poisoners continues to increase in the system. Because the existing defenses require parameterization of the number of attackers, they are ineffective when sybils are considered. We also run an experiment that considers training inflation attacks against defenses for federated learning, specifically multi-crum. In this experiment, the x-axis is a single increasing number of iterations in one federated learning setting, and the y-axis in this case is the L2 norm. But we also show the validation error in our paper, various statistics used to define early stopping criteria in a machine learning setting. Sybils have the ability to join the system and manipulate these metrics to arbitrarily extend the length of the training process. For example, this can be done very directly and throughout the entire training process. Sybils could collude ahead of time and decide to stop performing this attack once they're satisfied with the duration of prolonging they have induced. Or this could be done more stealthily over a long period of time to avoid detection from a hypothetical defense. Regardless of the Sybil strategy, a coordinated adversary has the ability to manipulate the length of the federated learning process and extend it with ease. This level of coordination and collusion in the training inflation attack has led us to more broadly consider Sybil strategies when attacking federated learning. We categorize these strategies along 3 dimensions: the diversity of the attack data and strategies used between Sybils. Are Sybils performing the same action all the time? Are they doing diverse things amongst one another? The coordination of the Sybils, how much state the Sybils are allowed to share amongst each other and how often they communicate. And lastly, the churn. We envision a hypothetical defense that may be stateful, and if Sybils have the ability to join and leave the system with ease, the effect of this state would be mitigated. After considering a variety of attacks on federated learning, as well as the potential of Sybil strategies to be used in these attacks, we categorize the existing work in attacks on federated learning into this table that intersects these 2 dimensions. For much more discussion and analysis of this work, please see our associated paper. For the rest of this talk, we're going to focus on the problem of targeted poisoning attacks from a group of uncoordinated Sybils. In addressing this, we design FoolsGold, a defense against this setting. When designing FoolsGold, we assume that the data is non-IID, as is the case for most federated learning deployments. We also assume that there is at least one honest client in the federated learning system. We also assume that the server can observe all the model updates. This is a limitation of our defense, as techniques such as cryptographic secure aggregation prevent the server from being able to see model updates individually, so they would not be compatible with FoolsGold. Broadly, FoolsGold works over 5 steps. First, the total model update history from each client is collected over the duration of the federated learning process. Secondly, the feature significance is measured over the process. This helps separate features that are not relevant to the poisoning attack and should not be considered as strongly when running FoolsGold. We then compute the pairwise cosine similarity between every single pair of clients in our system and normalize this cosine similarity through the inverse logit function to produce a weight in the 0-1 range. This weight can be interpreted as a learning rate. A weight of 1 means that the provided model update does not need to be modified or reduced, and a weight of 0 means that the provided update should be completely dropped from the system. This has the overall goal of penalizing contributions from clients that appear highly similar and perform this repeatedly over the federated learning process. We evaluate FoolsGold over a variety of attacks and a variety of different Sybil strategies. We consider a single attacker, many attackers, an overwhelming number of attackers, and other strategies in our paper. In this talk, we will only show 2 datasets, MNIST, the digit recognition task, and VGG Phase 2, the face recognition task that uses deep learning, but our paper has more datasets and attack variants, so I urge you to take a look and see for yourself. We first validate that FoolsGold does not interfere with the benign setting. So we execute a situation where there is no attack occurring in federated learning and compare federated learning to a system with FoolsGold and show that the results are similar. Next, we perform a targeted poisoning attack from 5 sybils on both datasets. This would be 33% of the clients in the system, and we show that FoolsGold is able to prevent a targeted poisoning attack in this case as well. When the number of sybils increases up to 99% for the MNIST dataset, FoolsGold is also able to defend this poisoning attack with effectiveness. Interestingly, the worst performance in FoolsGold is when there is only a single attacker. Because FoolsGold relies on client similarity, when there's only one attacker, there is no similarity to be measured for the Sybil attack, and FoolsGold performs badly in this case. However, in our paper, we show that FoolsGold can be combined with other existing defenses for federated learning to defend against both the single attacker case and cases in which sybils are used simultaneously, so not all hope is lost. One might ask us that because we assumed the non-IAD data setting, how much we rely on it when using FoolsGold to detect whether a client is malicious or not. For this, we perform another experiment where we measure and track the total model update over a VGG Phase 2 training process. For each client or sybil in the system, each row pertains to the weights of their final update summed over an entire training process. On the left is the non-IAD case, and you can see a diagonal black checkered pattern. This occurs because the data is non-IAD, so each client has only data for a single class and only contributes or primarily contributes updates pertaining to that class. In the full IAD case, where the data is evenly distributed amongst the 10 honest clients, it is a lot more difficult to distinguish these honest clients from each other, and they all appear largely similar. However, due to the nature of the targeted poisoning attack we execute on FoolsGold, it is still possible in both the non-IAD and the full IAD case to detect poisoning attacks, as sybils still appear similar in this setting. So even though we rely on the non-IAD cases, as the data becomes increasingly IAD, FoolsGold is able to distinguish between sybils and honest clients with some effectiveness. Next, we also ask whether an intelligent attacker has additional capability to defeat FoolsGold. Previously, we assumed that all sybils attack the system with the exact same strategy or the exact same underlying poisoned data set. What if the attacker is stronger? Perhaps they know how the FoolsGold algorithm works or some of the parameters used in the system, and let's assume they also have the ability to coordinate at every iteration and determine what their strategy should be before performing a targeted poisoning attack. Overall, this strategy involves bypassing FoolsGold by increasing the dissimilarity amongst sybils when performing the poisoning attack. 2 strategies we show in our work are that you can modify your model updates with orthogonal perturbations such that the dissimilarity is increased, yet the sum of the updates remains the same. And another strategy is to withhold the poisoning attack to avoid detection. This involves a mixed strategy where poisoning attacks are not always occurring, and this lowers the similarity detected by FoolsGold and helps them avoid detection. We run an experiment where the attacker has the following strategy. They run the FoolsGold algorithm locally and measure the similarity amongst the Sybil clients. For a fixed similarity threshold M, they only perform the poisoning attack if the similarity observed by FoolsGold is below this threshold. When M is too large, the attacker still poisons too often, and the attack is detected and prevented by FoolsGold. This is the entire right section of the figure shown, where the poisoning attack is detected. If the attack is performed too infrequently, it does not get detected by FoolsGold, but it is too weak to overpower the honest clients in the system, and the attack also does not succeed. That is the left blue area in this figure. Interestingly, there is a trade-off here, as with a lower threshold M, another way an attacker can bypass this system is by creating more sybils to achieve the same objective. However, this requires the cost of creating additional sybils, understanding of FoolsGold's parameterization, and some estimate of the honest client data distribution in the system. This is a very strong attacker that is able to defeat FoolsGold if they have this knowledge. Going back to the bigger picture, FoolsGold is just one solution for one section in the space of various Sybil attacks and Sybil strategies. And even FoolsGold can be defeated as a stronger Sybil adversary is assumed. We urge the community as a whole, when considering defenses and attacks for federated learning, to also consider the capabilities of sybils when defining the role of the attacker. In conclusion, we firstly identify that federated learning has a new threat model in which our adversaries can perform arbitrary compute. These attacks are made even stronger when considering sybils. We categorize the space of attacks on federated learning along the dimension of the objectives and the Sybil strategies, and also propose a new type of attack on federated learning called training inflation attacks, where resource consumption is the objective. Lastly, we present FoolsGold, one defense for a section of this categorization that defends against targeted poisoning attacks from uncoordinated sybils based on client similarity. Our code can be found at the following GitHub link, and I look forward to taking your questions both at the Q&A session and via email.